But anytime a force does work, if it's a conservative force, we can calculate a potential energy. So if we look at the work done by gravity as an object moves from here to here, which is a distance of h away, the work done is just the force of gravity times the distance times the displacement times the cosine of the angle, which is in this case theta is equal to 0, so cosine of theta is 1. So the work done is just Fg times h. Well, I know what the force due to gravity is. That's just mass times gravity, and then that h sticks around. So this term, the work due to gravity, that's an important term. That we associate mgh with something called the gravitational potential energy. Right? That's all that is. We've seen it already. We know where it comes from. We're just going to attach a special name to it. Right? So the gravitational potential energy of an object is just the object's mass times g times the height of the object. Now, this h thing is sort of special. This h thing is sort of, what is h? I could define h to be whatever I want. That's what we've been doing in this class so far, is when you're doing kinematics, you'd say, oh, we're going to set our coordinate system to be here, so that means the object has an initial height of 0, and then later on it maybe moves up, so it has a final height of something. So it's always, our heights and these sorts of position quantities are always sort of dependent on where we put our coordinate system. And this is no different. All right? This h is relative to something. So I can think of an example where we could calculate the potential energy associated with a particular object, and it may not be the same for two different scenarios. So imagine that, I think one of the common examples is you're getting ready to drop a water balloon on somebody's head. All right? And your buddy's down below looking out the window, all innocent-like. And he's, about to get hit by this water balloon that you're going to drop. And so it occurs to him that, in order to figure out if it's going to hurt, he would like to know how much energy this ball has. What's the potential energy stored in the ball, in the water balloon? So he says, well, I'm 3 meters below, so I calculate the gravitational potential energy of that ball to be the mass of the ball, mass of the water balloon times g times h. We know the mass of the water balloon is 1 kilogram because that's what I'm telling you it is. G is 9.8 meters per second squared. H is 3 meters. So if you run those numbers, you'd say that the potential energy of that ball is 29.4 joules. So when he drops that ball, I expect that I'm going to feel 29.4 joules of energy in some capacity whack me in the head. So that's what he says. But your other friend is just walking along, all minding his own business, when he sees the same water balloon and says, well, wait a second, I'm a little bit concerned about that water balloon hitting me in the head, so I'm going to calculate how much energy it's going to have. And your other friend is 5 meters away, so you do the same calculation. You get 1 kilogram times 9.8 meters per second squared, but times 5 meters. And you say, well, that's actually got 49 joules of energy. So the same balloon doesn't change position at all. Depending on who's looking at the balloon, sees the balloon have a different amount of energy. So what this tells us then is that it's not just some absolute value of the height that matters. It's the difference between the two heights, or it's the endpoints that matter. And you'll actually see this, while we won't always write the equations that we're going to deal with when we're talking about potential energy and conservation of potential energy in a form that makes this obvious, you can always manipulate the equations to put them in terms of a difference in height. It's never just the height that matters, it's the difference of height between two positions, an initial position and a final position. So you imagine if he drops the ball, it's going to start up here, And the amount of energy that you care about depends on the difference between this height, the initial height, and the final height, whether it's here or down here or wherever. So we're always going to care about height differences. So let's just do a simple example then and calculate the energy of something and kind of start to lead into conservation of energy. I'm going to use the text tool. So when we first started talking about energy, we talked about the energy of a few different things. And one of those things was a Big Mac. So imagine you just ate a Big Mac. And if you look back in your notes, you'll see that a Big Mac has, why did you do that? You'll see that a Big Mac has something like 2 times 10 to the 6th joules of energy. All right, if you convert the number of calories into joules, you'd get 2 times 10 to the 6th. So what you do to get rid of that extra energy that you just ate, you go rock climbing, because that's something that we all like to do. And so we ask the question, if all of the energy if all that energy gets converted directly to you going up, how high do you get? So how high does that energy allow you to get? So the picture is reasonably straightforward. We have broken legs. And you're just climbing up a rock wall like so. And you want to know, okay, if I start at the bottom here, basically, if I have 2 times 10 to the 6th joules of energy to spend to allow me to go up, how high am I going to get? In other words, how high off the floor do I have to be in order to have a gravitational potential energy of 2 times 10 to the 6 joules? Right? So pretty straightforward. We know that the gravitational potential energy in this case is 2 times 10 to the 6 joules. That's equal to the mass times gravity times height, where height is the difference between our starting point and our ending points in this case. So that allows me to calculate a height. So it's just 2 times 10 to the 6 joules divided by the mass. I like to use 80 kilograms if you haven't noticed, times 9.8 meters per second squared. If you do that calculation, what you get is something like 2,550 meters, which is, kind of depressing because I climb, and let me tell you, when I go climbing, I don't climb 2,550 meters. I go up and down a rock wall that's about 60 feet high, maybe 5 times. So we're not quite burning off the Big Mac. Now, of course, we made a pretty big assumption here that all this energy basically just goes straight into converting it into gravitational potential energy, which is not true. I mean, it takes our bodies a lot of energy just to be alive. So, I mean, this is a wildly simplified example, but it illustrates the point here. And not only does it do that, this is actually an introduction to conservation of energy problem. We actually did some conservation of energy here, which is what we're going to talk about next. I just didn't really show it. So I just want to point it out that we sort of cheated here when we did the math. We sort of made some assumptions that we didn't really address. All right, this is really a conservation of energy problem. So we're going to sort of talk about what really went on behind the scenes when I did this calculation. To do that, we're going to have to talk about conservation of energy. Now, you've already heard about conservation of energy. Energy cannot be created or destroyed. I said that the first day we talked about energy.
You probably heard that day one, first grade, right? I'm sure that back in your first grade, that's what you guys are talking about. For me, it was second grade. So in this class, though, we're gonna narrow that down a little bit. Now, this always applies. You can't create or destroy energy, but when you hear conservation of energy, sometimes it takes on different sort of forms. You might hear conservation of energy, or you might hear conservation of mechanical energy, or something like that. So I'm going to write it in a couple different ways. So the first way I'm going to write it is I'm going to say, if there are no non-conservative forces, acting on the object that you are particularly interested in. E.g., of course, we know one of those is friction. So if there's no friction, air resistance, tension, engines, etc., we can write down the initial energy of the system is equal to the final energy of the system. Right? This is the most fundamental statement of conservation of energy. This is always 100% true. Even though I quantified it here with this non-conservative forces, the energy initially in some system is going to be equal to the final energy of the system. It just so happens that we may not be able to keep track of the energy very well, like friction. Like I said, we have trouble keeping track of friction. We have trouble keeping track of heat, at this point in this class. So one way to state this is that the total energy of the system is constant. So if you have no non-conservative forces, the total energy of your system doesn't change from point A to point B to point C, time 1 to time 2, time 3. Okay? If there are conservative forces, we have a very similar equation where we're looking at the difference between how the final energy of the system compares to the initial energy of the system. But if you take the difference, that's got to be equal to the work done. And this is the total work. Yeah. Thank you. The total work done by non-conservative forces. So I want to take a minute. I don't want you to say, well, there's two equations for energy conservation. All right? I don't want to confuse. I want to try to rectify these two equations. So energy is always conserved. Okay? It just so happens that in mechanics, in this class, like I said, we don't know how to track certain types of energy. So we have this work term. Now, when I started talking about work on day one, I said work is just energy. So really, this work term is just a form of energy, and it can go into one of these E terms. But we have all these nice little other equations that we can stick in these energy terms. So we usually treat the left-hand side of this equation as those things like kinetic energy and potential energy, well, gravitational potential energy, spring potential energy. And then the right-hand side of this equation is reserved for all those other things. So it's friction and air resistance and work done by an engine, work done by me pulling on a sled. All those other things that we don't have nice little 1/2 mv squared equations for. So these equations are essentially saying the same thing. This one just allows us to sort of be a little bit more quantitative when we're talking about energy. Because we have another equation for work, it's a force over a distance. And we have other equations for energy, like kinetic and potential. All right, so this is really what we're going to be dealing with in this class, even though it says the same thing is up here. Okay? Does that make sense? It's really important to me that makes sense, because sometimes this equation will be exactly that, because work is 0. There's no non-conservative forces. You're just writing that down. All right? But really, they're saying the same thing. All right, so if we go back and look at our example then of the person climbing, what we said then was we were really looking at a difference in energy. We said initially, we got all of our energy from a Big Mac. So we had 2 times 10 to the 6th joules worth of energy. All right? We used all that energy up to climb a wall. So the final energy, not E, so J, the final energy is conserved, so it's still 2 times 10 to the 6th joules, but all that energy went into potential. It all went into gravitational potential energy, MGH. Okay? So these two are the same because energy is conserved. It's just converted into gravitational potential energy. All right, so really what we did was we solved an E initial is equal to E final equation. We just sort of skipped a few steps. So when you're working on problems, this is like a, okay, specifically for you guys to go home at night and think about when you're working on your problems. Most of the time, you're going to write something like this. Conservation of energy says this. The final energy is equal to the initial energy. We know that if a system's moving, it has kinetic energy. If it's at some height, which is whatever I want it to be, it has some initial gravitational potential energy. That all gets converted into kinetic energy plus some change in gravitational potential energy. So this equation you will see many times in your homework. Now, of course, we're missing things here. This only accounts for kinetic energy and gravitational potential energy and the changes of those two forms. All right, so you can imagine this is a good example. If I have a ball and I toss the ball and you want to analyze the motion of the ball right after it leaves my hand. So initially it has lots of velocity. We say gravitational potential energy is small. It moves up, its velocity goes down, but all that velocity, that energy coming from the velocity, coming from the kinetic energy, goes into gravitational potential energy. So as the ball is moving up and then it comes back down and you convert it back into kinetic energy. Okay? Now, of course, in that simple example, we don't have things like springs. We don't have friction. We don't have engines. We don't have humans. We don't have chemical reactions. All right, all different forces that we can't account for, that aren't accounted for here, and that we have to account for in some other place, be it potential energy or some generic work term. Okay? So, but generally, it's not a bad idea to start here and then go forward and look at these other possible sources of energy. So my suggestion when you're doing energy homework, start off by drawing a picture. And list the types of energy that are important to the problem. Look at your problem. Is something moving? Then you have kinetic energy. Is something changing its position? Then you probably have gravitational potential energy involved. Is there a spring? Well, then you have a spring involved. All right. Is there friction? There's work done by friction. Make a list. After that, you pick up where you left off and you solve using conservation of energy. And step 4, as always, make sure it makes sense. Okay, so that's sort of my thought process of going through solving conservation of energy problems. I mentioned this yesterday. The types of problems that you encounter with conservation of energy, similar to the types of problems that you've encountered so far with dynamics and kinematics. Typically, using an energy approach to solving those problems is easier. So that's really nice. That's an added benefit of doing this sort of thing. So with that said, let's go ahead and we'll tackle some examples. All right, so the first one is sort of a problem that you could envision seeing back in chapter 3 or 4. And that is, I don't like that curve. All right,
imagine there's a castle on a hill, and you have a catapult that is going to launch a rock, and you're trying to hit that castle. And the castle is 200 meters off the deck. And you know that you can launch this thing with some velocity v, or some speed v. All right? So let me word the problem out. If you have a catapult, and it can launch a stone, which has a mass of 10 kilos, at a speed of 35 meters per second. The question is, can it reach the castle? Now, hopefully you look at this problem and you say, kinematics, I could do that with kinematics. I know the initial velocity, you'd have to, and I can figure out if it can reach, if it could reach 200 meters, right? So this is something you totally do with kinematics. But you could also do this with energy. If I write down my conservation of energy, the equation always looks like this. The initial energy is equal to the final energy. Well, the types of energy that I might come across in this problem, it has an initial speed, so I know there's going to be some kinetic energy. I'm looking at that speed being converted into altitude, so I know that there's going to be gravitational potential energy. I'm not worried about the catapult. I already know the catapult's giving me some speed v, so I don't care. All I care about is the catapult's basically not even in this picture. So there's no springs. We're not taking into account friction or air resistance. This is all I have. So I have that really simple equation that I showed you just a second ago, which is 1/2 times the mass times the initial speed squared plus the mass times gravity times the initial height is equal to 1/2 times the mass times the final speed squared plus the mass times gravity times the final height. All right, so what I'm really after here is I'm after the final height. I'm trying to get to 200 meters, but I don't know if that's the final height. So what I'm doing is I'm taking all of my energy initially and converting all of that kinetic energy into some potential energy. I'm at will to choose where I want my initial height to be or my final height. I'm going to go ahead and say that height is 0 right at the launch point, which means that this guy goes to 0. And I know that when the velocity is 0, that's as high as when the speed is 0, that's as high as that ball is going to go. At that point, every last drop of energy has been converted into gravitational potential. So I'm left with this equation that says the initial kinetic energy is equal to the final potential energy. So if I go ahead and solve for the final height, I notice that the mass cancels out. Mass isn't important. That's good because when we were doing kinematics, you certainly didn't account for mass. And what I get is the final height is equal to v initial squared divided by 2 times gravity. So if I plug in my numbers, I know my initial speed is 35 meters per second. I square that. I divide by 2 times 9.8 meters per second squared. And if you solve for that, you get 62.5 meters. So no, I can't hit the castle. In this problem, what did I basically assume the trajectory of the ball to be? Yeah, it has to be straight up. So I'm assuming that this is fired straight up because I'm taking all of my initial speed. I'm saying that's all going into the upwards direction. And that's being transferred into the height of that stone. Surely if I had shot the ball straight out to the right, my final height is not going to be higher than it was launched. Okay, so in this problem, I'm assuming it's going up. So not only would it not get high enough if I was shooting it straight up, I certainly couldn't make it to the right at all. All right, so I'm really not going to hit that castle. All right? Yeah, Chloe.
Can you just explain why final velocity was 0 again?
The final velocity is 0 because I know that if the final velocity is 0, that all of my energy has been converted into the height of the projectile.
Okay.
If my final speed was not 0, then I wouldn't have reached my maximum height. All right, so in other words, if you're watching this ball as it's going up, actually let me draw it down here. So initially, you have the stone, it's being fired up with some velocity. So you have kinetic energy is a maximum, and gravitational potential energy is 0. All right, a little bit later, the rock's left, the speed's gone down, still has some kinetic energy, sort of a medium amount. Gravitational potential energy now is also a medium amount. And then a little bit later, the ball gets up to the peak. The kinetic energy is now 0 because it stopped for a moment. A moment in time it stopped, and now I know that my gravitational potential energy is a maximum. After this point, it comes back down. All right, so only when the velocity is 0, when the speed is 0, that's when I've reached my maximum position, my maximum height. So if my maximum height in this particular problem is less than 200, I know I'm never going to get to 200. All right? But notice one thing. If I add these two together, if I add kinetic energy and the potential energy together, how do the values compare from one time period to another? All right? In each case, they're constant. If I add kinetic energy to U, to the potential energy, it's constant throughout this entire time period. Never changes. The total never changes. You're just converting from one type of energy to another type. Okay? Mallory, you had a question?
Not right now.
Okay. All right, so that's the key to this problem. It's the total energy is constant. Again, we've assumed there's no air resistance. All right, so there was no work done by a non-conservative force. Had we accounted for air resistance, then we would have lost some energy because we would have moved some air molecules and heated the air up or something like that. All right, let's do another one. Get into some roller coasters now. All right, so you have a roller coaster in this problem. And it rides over a couple of hills. I want to know how fast does it ride over another hill. And I'll give you some information here. Let me draw the picture. So the picture is something like this. You have a roller coaster. All right, at the top of this hill, the speed is 10 meters per second. And I know that that hill is 15 meters off the ground. And I want to know the speed as it goes over this hill, which is 8 meters off the ground. All right. So again, if I list the energy, the types of energy I expect to encounter, again, it's moving, so there's some kinetic. There's going to be a change in height, so I know that there's going to be some gravitational potential energy involved. No springs, no friction, no air resistance, no motors. That's all we're dealing with. So again, just a simple two types of energy problem. So now I write down my conservation of energy. The initial energy is equal to the final energy. There's no non-conservative forces, so there's no work done by non-conservative forces term. And I write an equation that looks very similar to the one I solved in the previous example. Just 1/2 mass times the initial speed squared plus mass times gravity times the initial height. That's equal to 1/2 times the mass times the final speed squared plus mass times gravity times the final height. On this problem, it's not really obvious to me that any term goes to 0. In fact, I have two heights here. I have one speed, and I'm solving for another speed, so it doesn't seem like any of these terms are going to go away. That's fine. They don't have to go away. What we're after, though, is this final speed. So I want to solve for that final speed, and I can do that. So let's just move that whole thing to the right-hand side. Vf squared, that's equal to 1/2 mass times the initial velocity squared plus mghi minus mghf. And I write it like this to point out something that I said earlier. And that is that we're always concerned about this difference, the difference in height. Notice that I can factor out n mass times gravity. And then all I care about is the height difference. It doesn't matter what the initial height is. It doesn't matter what the final height is. All that matters is the difference. That just tells me mathematically that I'm free to choose a coordinate system however I want. In this case, the way that I've drawn this picture is this is y is equal to 0, this dashed line. But I could arbitrarily come along and say, no, I choose this to be equal to y is 0. In that case, y is equal to 0 here, which means my final height, or my initial height, I'm sorry, is just going to be 7 meters. All right. So all that matters is this difference. It doesn't matter what I call y0, just like in all of our other problems, because you always have this difference term. All right. So with that said, I can go ahead and solve this thing. Again, mass cancels out in this problem, which is a nice benefit. If I divide through by 1/2, I cancel out those two things and I add a 2 over here. Now what I'm left with is v final is equal to the square root of the initial velocity squared plus 2g times the height difference. In my problem, I use different, in my notes, I use different numbers, so I don't actually know what this is going to end up being. So we get we get 10 meters per second. We're going to square that, and then we got to add on 2 times 9.8 meters per second squared times a height difference of 7 meters. That's equal to 100 plus 20 times 7 is 140. So what is that? Who's got a calculator really quick? It's got to be something like, the square root of all that is something like, I don't know, 17? Is that about right? Just estimating, top of my head.
$15.4.
15.4, sounds good. So the answer is 15.4 meters per second. There you go.